Simplifying radicals containing imaginary numbers. Let's begin with an algebra review. Recall the properties of radicals that are shown here in the box. For a values and b values that are greater than or equal to 0, the square root of a times the square root of b is equal to the square root of a times b. The second property is the square root of a divided by the square root of b can also be rewritten as the square root of a divided by b. And the third property is the square root of x raised to the 2n power, meaning it's an even power, is equal to the absolute value of x to the n. And this mainly occurs when our initial n value, or the resulting exponent of our variable being raised to an exponent, is odd. When it's even to even, you don't have to worry about the absolute value being involved. But when it goes from even to odd, you do. So let's try to use these properties that are defined for real numbers to simplify the following examples. For a, we have the square root of 80. So that's going to be square root of the perfect square, or the highest perfect square that goes into 80 is 16. And it's multiplied by 16 5 times to get 80. So then we square root 16. And we square root 5. We can simplify. The square root of 16 is 4, and we are left with 5 inside of the radical. Now let's look at question B. We have the square root of the quantity 12x squared. Well, that's equal to the square root of 4 times 3 x squared. And that's going to be equal to the square root of 4 times the square root of 3 times the square root of x squared. We can take the square root of 4, that's 2. The radical 3 is going to stay there. And now the square root of x squared is just x. So this is going from an even exponent inside of the radical to an odd, so we need to make sure we include the absolute value in our answer. Now let's look at our next problem. We have the square root of 64 m to the 4th power n squared. That's going to be equal to the square root of 64 times the square root of m to the 4th times the square root of n squared. Square root of 64 is 8. When we square root m to the 4th, we get m squared. So we went from even to even, so we do not need the absolute value. But now when we do the square root of n squared, that's just going to be n. So we need to put it inside of the absolute value because we went from an even exponent to an odd exponent. Now let's look at our last problem. We have 4 times the square root of the quantity 125 x to the 3rd y squared. So we have the square root of, we can rewrite 125 as 25 times 5. And then we're going to have x to the 3rd y squared still in there. So now we're going to have the square root of 25, the square root of 5, the square root of x squared times x, and then the square root of y squared. Now the square root of 25 is 5. And I forgot to put the 4 in front and bring it down. So we have 4 times 5. We have a square root of 5 still remaining. Now the square root of x squared is just x. And we also have an x remaining inside of the radical. And now the square root of y squared is just y. Now where does the absolute value have to go? It has to go around the y because we went from an even exponent to an odd exponent outside. Since our exponent for our x variable was odd to begin with, we do not have to worry about the absolute value. The final answer to this problem is going to be 20 x times the absolute value of y times the square root of 5x. And here are the solutions to these 4 example problems, and they do indeed match the solutions that we found when we worked the problem out. Again, the key point to remember, especially with property number 3, is when you go from an even exponent inside of the radical to an odd exponent outside of the radical, you need to have an absolute value. So again, here with the square root of x squared, we went from even to odd. With m to the 4th, we went from even to even, so we actually don't need the absolute value. With the n squared, it became n to the 1st, so we need absolute value around that one. And then in part D, remember we had x to the 3rd, so we don't need to have an absolute value around the x that comes out of the radical, because there's another one that remains inside of the radical. Now with y squared, because it was even and it went to odd, that's when we need the absolute value around the y. The last set of examples that we worked through involved simplifying radicals that contained positive radicands, meaning the number inside of the radical was always positive. Now the properties of radicals apply to real numbers. To manage negative radicals, there is one additional property that we will need to embrace, and that is that a has to be greater than 0. And whenever we have a negative a, we have to first split it into the square root of -1 and the square root of a. And the square root of -1 is I, and then we still have the square root of a. In other words, you need to take the I out of the radical first before you continue simplifying. Let's go through these 4 examples to further explain and get experience with it. So we have the square root of -16. We can rewrite this as the square root of -1 times the square root of 16. The square root of -1 is I, and the square root of 16 is 4. And then if we rewrite it and put the coefficient first, we will have 4i as our final answer for this problem. Now let's look at the next one. We have the square root of -48. That's the square root of -1. And now other factors of 48 are 16 and 3. So we have an I, we have a 4 from the square root of 16, and we have the square root of 3 still remaining in the radical. And that's our final answer in this problem. Now let's look at the next one. We have the square root of -200. So we first have to rewrite it as the square root of -1 times the square root of 200. So we have an I times, now the square root of 200 can be rewritten as the square root of 100 times the square root of 2. And the square root of 100 is 10. We have the I out in front, and we have square root of 2 remaining inside of the radical. And that's our final answer for this problem. Now let's look at this next one. Some of you may be inclined to be like, hey, -16 times -4 is going to be +64, and the square root of 64 is 8. Well, that property of the square root of AB being equal to the square root of A times the square root of B only applies for A and B values that are greater than or equal to 0. Since A and B are both less than 0, we have to take the I out first. So we need to first rewrite the square root of -16 as I times the square root of 16 times, and then the square root of -4 as I times the square root of 4. So now we have 4i times 2i, because the square root of 16 is 4, and the square root of 4 is 2. So now we have 8i squared, which is equal to 8 times -1, which is -8 as our final answer. And here we see the final answers to each of these 4 problems, and they do match the solutions that we found when we worked them out. Again, the key thing to remember is whenever you have a negative radicand, you need to take the I out first and then deal with the remaining radicand value that would be then greater than 0. Here are some more examples where we are simplifying radicals containing negative values. So let's simplify each of these. We first have the square root of negative 15 times the square root of negative 30. We first need to pull the I out of each of these radicals. So we have I times the square root of 15 times I square root of 30. The next thing we can do is multiply our I values together to get I squared, and also multiply the remaining radicands together. 15 times 30 will end up being 450 inside of the square root. Now, 450 does have a perfect square that divides into it nicely, and that's 225, and it divides into it twice. So we still have, and then we're going to square root both of these. So we still have the I squared, but now we have 15 I squared, and then the square root of 2 remaining. Now I squared can be rewritten as negative 1, so we have 15 times negative 1 times the square root of 2. And now when we multiply 15 and negative 1 together, we have negative 15 times the square root of 2 as our final answer in this problem. Now let's look at the next problem, the square root of the quantity negative 16x squared. Again, first step, because we have a negative in there, we have to pull the I out. So we have I times the square root of 16x squared. That means we are taking the square root of 16 and the square root of x squared. Now the square root of 16 is 4, so we have 4i, and now the square root of x squared is x, but because the coefficient out in front here is positive, we need to put this x inside of the absolute value. It went from an even exponent to an odd exponent, and we only want the positive answer. So our answer to this one is 4i times the absolute value of x. And here are the solutions to these two examples, and they do match the solutions that we found. Now let's try some more practice with simplifying radicals containing imaginary numbers. The first problem that we have here is the negative square root of the quantity negative 45a squared. All right, so we want the negative, that's going to continue coming out. And now our radicand is also negative. Because the radicand has that negative coefficient, we need to bring our I out right away. And we are left with the square root of 45a squared. Now let's look at the 45. Is there a perfect square that divides into 45 nicely? Yes, there is. 9, and it goes in 5 times. So we square root both of these. We also have the negative I that we are going to bring down, and we have the square root of a squared remaining. When we square root 9, we will get 3. So we have negative 3. I'll put the I, I'll leave some space there. 5 is going to remain inside of the radical, and now the square root of a squared is a. And since we are going from a positive a squared value, and it's even as the exponent, to an odd exponent, we need to bring the a out inside of the absolute value. So we have negative 3 times the absolute value of a times I times the square root of 5. As our final answer in this problem. Now let's look at the next one. We have the square root of the quantity negative 3m to the third power times the square root of the quantity negative 27m. We're going to begin by first bringing the i's out. So we have I times the square root of 3m to the third, and we also have another I times the square root of 27m. So we have I times I, which is I squared. And now we can multiply our radicands together. So that'll be the square root of 81m to the fourth. Now the square root of 81 is 9. So we have 9 I squared. And we have, from m to the fourth, we now have m raised to the second power. And now I squared is negative 1, so we have 9 times negative 1 times m squared. So we have as our final answer here, negative 9m to the second power, or m squared. Here are the solutions to the additional practice problems that we worked through, and they do match the solutions that we found. Now this one was solved in a slightly different way, but it is absolutely valid. They first brought out the i's, and they also brought out a 3 because 27 can be broken down into 9 and 3. So they brought out a 3i here and the I from this first radical. And then they multiplied 3i times I, which is 3i squared. And then they multiplied 3m to the third times 3m and got 9m to the fourth. And the square root of the quantity 9m to the fourth is 3m squared. So you had the 3 out in front times another 3, which is 9, have the I squared and then the m squared, and then I squared is negative 1. So we have negative 9m squared as the final answer.